Okay, in this video, we're going to talk about section 2.2, dealing with more things that are related to functions and graphs. In the first section, we talked about the basics of functions and graphs, things like what a relation was, what a function was, and how to determine whether a relation is a function. Also determine how a equation, whether or not an equation was a function. Also, we determined whether or not a graph was a function. And we did talk about function notation as well. In this case, there's more things that we're going to talk about that are related to functions and graphs, like identifying intervals in which the function increases, decreases, or is constant, locating relative maxima and relative minima, also identifying even and odd functions and recognizing their symmetries. And we're going to understand and use piecewise functions. So this is just more stuff on functions and graphs. Okay. So let's talk about increasing and decreasing functions here. In the blue box that you see here are three different types of functions. One, it could be increasing from left to right, as you can see here on some interval from, let's say, A to B. Also, we have a graph that's decreasing, and if you see decreasing, that means that the graph is falling from left to right on some interval. And constant means that the line is a flat line. Okay. And we always use open intervals to describe whether functions are increasing, decreasing, or constant. And we use only the x coordinates and not the y coordinates. So let me kind of summarize something that I shared with my lecture classes. Okay, and that's this right here. The three guidelines. Number one, you want to read the graph from left to right along the x-axis. Okay, that's number one. Then second, you're going to always use x values. Not going to worry about the y. You always use your x values, which are on the horizontal axis, and then always use parentheses. Okay, we're not looking at the endpoints. We always use the parentheses. So here I drew a graph that's increasing on an interval, which I call from A to B. Also decreasing, doesn't mean it's falling in between this interval A to B. And also constant is a straight line. Anything increasing means that it's rising from left to right. Okay. So if you want to, you can add this in your notes by pausing the video and copying this down if you like. All right, but we're going to use that to do some examples here, like this one. Here I want to state the intervals on which the given function is increasing, decreasing, or constant. Okay, so what I'm going to do here is write down this, the intervals that are where this graph is increasing or decreasing or constant. All right, now the way I'm going to do this is I'm going to take a, let's say a clean sheet of paper, cover the graph, and then we're going to move this graph from left, we're going to move this paper from left to right along the x-axis to see where it is increasing or decreasing or constant. So when I do this, so I'm going from left to right. Now that arrow down here, that means this goes on and on forever. But when we go from the left, we see it's increasing, still increasing, still increasing. Notice right here, it reaches its highest point. It maxes out at x is equal to -1. So from the interval of -infinity up to -1, this graph of f of x equal to x cubed minus 3x is increasing. So we can say that it's increasing from -infinity to -1. All right, next I'm going to do this. I know we've got -1 here. I'm going to cover up this sheet, right? Cover up this graph right here. We know it maxes out at -1, but after -1, notice what's happening. It's decreasing, decreasing, still decreasing, decreasing, and then it starts to turn at 1. So between -1 and +1, you're going to see that graph of f of x equal to x cubed minus 3x that is decreasing. Okay, so this graph is decreasing between -1 and 1. And we write this in interval notation using parentheses, no brackets. And then after 1, pretty much you can see what's happening after 1 is going back up. It's increasing onto infinity. So under increasing, I'm going to use the union symbol, 1 to infinity. And notice there's not constant anywhere. There's no straight line in this graph. So that means we can just put the word none. Okay. So those are the intervals where it's increasing from -infinity to -1, and from 1 to infinity. It's decreasing between -1 and 1. It's constant nowhere. Okay. All right, here's another example. Let's say we want to use this graph to determine the intervals on which the function is increasing, if any, the intervals on which the function is decreasing, if any, and the intervals on which the function is constant, if any. Okay. So let's go ahead and answer part A, where it's increasing. So let me cover the graph with a sheet of paper and move that sheet of paper from left to right. Well, we see that it's going to be increasing, still increasing, continues to increase and continue to increase and to continue to increase until it reaches its highest point. All right, so its maximum point is reached at x equals 2. So from -infinity up to 2, we can see that graph is increasing. So here's the interval, -infinity to -2. That graph is increasing. Now, if I continue after not -2, +2, -infinity to 2. And then after 2, what's happening here? It's decreasing onto infinity. So from 2 onto infinity, this graph is decreasing. Okay. And of course, in part C, the intervals on which the function is constant, we just say none. Because there's nowhere that you see a straight line anywhere in that graph. Okay. Now, here's another example. Let's say I want to use the graph to determine the intervals on which the function is increasing, if any, the intervals on which the function is decreasing, if any, and the intervals on which the function is constant, if any. Okay. So again, I'm going to cover the graph up with a sheet of paper, and then I'm going to move this sheet of paper from left to right. Well, notice this graph is decreasing, 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 and then it bottoms out. at x is equal to 3. So from negative infinity up to 3, it's decreasing. So this is the answer to part B. Negative infinity to 3, because it's decreasing. And then after 3, notice what's happening here. We have a straight line from 3 on out to infinity. That means it is constant. It's not going up or down. It's just remaining constant. It's just a straight line, a straight line. So from 3 to infinity, the function is constant. It's just a straight line. And part A, we just say none because it's not increasing anywhere. It's not going up or down. Well, going up, I should say. Okay. All right, next we'll look at relative maxima and relative minima. Now, these are just the formal definitions of relative maxima and relative minimum. A function value called f of a is a relative maximum of f if there exists an open interval about a such that f of a is greater than f of x for all x in that open interval. So here, this is your relative maximum. In other words, that's going to be the y value at a peak. And then number 2, a function value f of b is a relative minimum of f if there exists an open interval about b such that f of b is less than f of x for all x in the open interval. Okay. So in other words, here's your relative minimum here. That's going to be the lowest point or the valley on that graph. Okay. And I can share this with you. Now, if you take a look, I gave it a better definition. It's a y value at a peak. So when you're looking at a relative maximum or relative minimum, you're dealing with the y value. So the relative maximum is the y value at the peak, as you see here. And the relative minimum is the y value at a valley. That's going to be down here. And keep in mind that your relative maximum or relative minimum will be y values, not the x, y values. Okay, so let's go back to this and we'll look at example 4 on this handout. It says here, use a graph to determine the following. In part A, you want to find the numbers at which f has a relative maximum and what are these relative maxima. Also, you want to find the numbers at which f has a relative minimum and what are these relative minimum. Okay. Now let's look at this graph right here. Let's start with the relative maximum. That's going to be the highest point on the graph. And I apologize that this is not the best looking graph that you see here. But here, the highest point, if you look at it, it will be this point right here that I'm putting in red. So that's the relative maximum. Now, we want the x value where this relative maximum occurs. And that x value that we're looking at here for this case would be at x is equal to 1. So at x equals 1, that is the relative, that's where the relative maximum occurs. And our relative maximum is going to be that y value for that point. Here's that point. the y value for that would be 5. So the relative maximum is 5. It occurs at x is equal to 1. Now, part B, find the numbers at which f has a relative minimum. And what are these relative minima or minima? Those are the lowest points on this graph. I got the lowest point here and here. Notice I got 2 relative minima. Where do they occur? So here's one relative minimum, and it occurs at x is equal to, in this case, x is equal to 0. So at x equals 0, and the other relative minimum is right here. It occurs at x is equal to 2. So at x equals 0 and x equals 2, we have a relative minimum. And what is that relative minimum? In this case, they're both at the same y value, which is at 1. So the relative minimum is 1. Okay, and here's one more example of this. Now notice we're given a graph from a TI-83 or an 84 plus calculator. The graph and equation of the function are given. In this case, we got f of x equal to 2x cubed minus 3x squared minus 12x plus 3. And in this case, we want to, part A, use the graph to find any values at which f has a relative maximum and use the equation to calculate the relative minimum for each value. Okay, so let's look at this here. I'm going to put part A down here. Now, let's find our relative maximum. That's the highest point. That's going to be up here at that point right there. Now, notice that our x-axis is from -5 to 5 in increments of 1. Okay, so that means this goes out to -5, then -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. So in this case here, the x value where this relative maximum occurs is at -1. Okay, so that means at x is equal to 1, our relative maximum occurs. So what is that relative maximum? Unfortunately, you're not going to be able to see it on this display. However, we have the function f of x equal 2x cubed minus 3x squared minus 12x plus 3. We can use that to evaluate what our relative maximum is going to be. Okay. So here, we're going to evaluate f of -1. And this should be -1, not 1. Okay. So we evaluate what the y value is at x is equal to -1 by substituting each x with -1. So f of -1 would be this: 2 times -1 cubed minus 3 times -1, and that's squared, minus 12 times negative 1 plus 3. So in this case, if I cube the negative, it's going to be negative. So negative 1 cubed will be negative 1 times the 2 in front would be negative 2. And then minus a negative and u squared will be positive. So negative 1 squared will be 1 times the minus 3 will be that minus 3. And then minus 12 times negative 1 will make that a plus 12. And then plus 3. Now, if I simplify this, I know that negative 3 and a plus 3, that adds to 0, so that's gone. And then I had negative 2 plus 12 would be 10. Okay? So this is the relative maximum. That relative maximum is 10. It occurs when x is equal to negative 1. Okay? Now the B part is this. Use the graph to find any values at which f has a relative minimum and use the equation to calculate the relative minimum for each value. Well, the relative minimum is that lowest point or the valley. That's down here. And the x value where that relative minimum occurs is at x is equal to 2. Okay. So at x is equal to 2, that's where our relative minimum occurs. Now let's find what that relative minimum is by using that f of x function and substituting each x with 2. So we're going to evaluate f of 2. That's going to be equal to this, 2 times 2 raised to the third minus 3 times 2, that's squared, minus 12 times 2 plus 3. All right, when I simplify this, I'm going to bring this 2 down. 2 cubed is 2 times 2 times 2, that's 8, minus 3 times 2 squared, 2 times 2, that's 4, minus, and I'll go ahead and multiply 12 times 2, that'd be 24 plus 3. And now 2 times 8 is 16, minus 3 times 4, which is 12, minus 24 plus 3. Okay. Now 16 minus 12 is negative 4. I mean, just plain 4. 4 minus 24 is negative 20. Negative 20 plus 3 is negative 17. This is your relative minimum. Okay. Okay, so in this case here, you have to use that function that was given to you to find out what your relative minimum and relative maximum are going to be. Because you're not going to directly identify from this calculator display. All right, next we'll look at even and odd functions and how they're related to symmetry. All right, first let's talk about even functions and odd functions and their definition. An even function is this. If you have f of negative x and you simplify and you get the original function f of x, that means you have an even function. Okay. So in other words, you're going to be given an f of x function. You want to substitute each x with negative x and simplify. And if the right side of the equation does not change, you have an even function. Now for an odd function. substitute the x with negative x in f of x, and if you get the opposite of the original function, that's negative f of x, you have an odd function. That means every term on the right side of the equation changes its sign. Every term on the right side of the equation changes its sign. Now let's look at a few examples of what this means. In part A, you got to determine whether each of the following functions is even, odd, or neither. Let's say we got f of x equals x squared plus 6. I want to know if that's an even or an odd function or neither. In this case, if I substitute negative x for x, this is what I'll have. Negative x, and that's squared, plus 6. And now a negative and u squared will be positive. So negative x and we squared is negative x times negative x, which is going to be x squared plus 6. Compare that to what f of x is. It's exactly the same. I did get the original function that I started off with. So this is considered to be an even function. Okay. All right, here's another example. Let's say here we got g of x is equal to 7x cubed minus x. G of x is equal to 7x cubed minus x. Well, let's start by substituting each x in g of x with negative x. So this will be 7 times negative x, and that's going to be cubed, minus the x will be replaced with negative x. And let's simplify. We're cubing a negative, so that means it's automatically going to be negative. So I pull the negative in front, and this will be 7. This x is going to be raised to the third power. So I got negative 7x cubed. Minus a negative x will be written as plus x. Compare that to what g of x is. It's not even because I didn't get the original function that I started off with. But if you look at g of x and g of negative x, the sign, each term changed to the opposite sign. I started off with 7x cubed. I ended up with negative 7x cubed after substituting the x with negative x. I started off with a minus x. I ended up with a plus x. So that means this function is odd. This will be an odd function. And then we got h of x equals to negative, h of x equal to x to the 5th plus 1. Here I want to determine whether that function is even or odd, or neither. So again, we substitute the x with negative x. This will be negative x, and that's going to be raised to the 5th, bring down the plus 1. Again, a negative to an odd power will be negative. So I can pull the negative in front. The x will be raised to the 5th, and then I bring down the plus 1. Compare that to what h of x is. It's not odd because I didn't get the original function that I started off with. And it's not even because only the first term changed to the opposite sign. That plus 1 remained the same. For it to be odd, each and every term must change to the opposite sign. Only the first term did. The second term did not. So this is an example of a function that is neither odd nor even. Okay. All right, now let's briefly talk about symmetry. Okay. First, for even functions and y-axis symmetry. If our f of negative x comes out to be the original function, it's going to be symmetric with respect to the y-axis. Okay, so this graph that you see here is a graph that is symmetric with respect to the y-axis. In other words, here's my y-axis here. If I fold this piece of paper along the y-axis, the right side of this graph has the mirror image of the left side of the graph. In other words, the right side of the graph will lie on top of the left side of this graph if I was to fold the piece of paper along the y-axis. Okay. Now for odd functions in origin symmetry, if I substitute the x for negative x in f of x, and I get the opposite of the original function, that graph will be symmetric with respect to the origin. And this is a graph that would be symmetric with respect to the origin. In other words, if I take this top part of the graph that's on the right side of this y-axis and rotate it, it would lie directly on top of this bottom piece of the graph. Okay. All right, so that means that the odd function would have origin symmetry. Okay, that's what we mean by even and odd functions with y-axis symmetry. Well, even functions with y-axis symmetry, odd functions have origin symmetry. And we're going to talk more about that when we get into graphing quadratic functions and also graphing rational functions as well in future videos. Okay, last thing we'll talk about in this video is a piecewise function. Here, a piecewise function is defined by two or more equations over a specified domain. Okay. Now, many cellular phone plans can be represented with piecewise functions. Also, income tax withholding, the amount that your employer withholds for federal income tax, that too can be a piecewise function if you think about it. Okay. Because if you kind of look at the tax table, then pretty much the amount that you earn, your gross earnings, can be determined by using that tax table. And it is in the form of a piecewise function. All right, in example 7 here, this describes a cellular phone plan where we have C of t is equal to 20, and we only use that if your t, which is the time, is between 0 and 60 degrees inclusive. Or 20 plus 0.40 times the quantity t minus 60 if your t is greater than 60. Now, if you were to interpret that in words, a cell phone plan like this would be like $20 for the first 60 minutes plus 40 cents for each additional minute. Okay, so in these two examples, we're going to use that to interpret each of the following. Like in part A, the cost for 40 minutes on this cellular phone plan. Now, this value right here is going to tell us which one of these we need to use, either the first or the second. Now here, the t is 40 minutes. That's between 0 and 60. So we have to use this function right here. And in this case, it's just 20. So C of 40, or the cost of a cellular phone plan after 40 minutes, would just be $20. And we're done with that problem. Okay? Because it's your t value is going to, the value of t is going to tell you which one you need to use. And for the cost for 80 minutes on a cellular phone plan, this is part B. 80 is your T. Notice that it's over 60. So we must use this 20 plus 0.40 times the quantity T minus 60. So here the cost of 80 minutes is this 20 plus 0.40 times T will be substituted with 80 minus 60. And then we simplify. In the parentheses, 80 minus 60 will be 20. So this will be 20 plus 0.40 times 20. 80 minus 60 is 20. And then if I multiply 0.40 times 20, that will be 8. And then 20 plus 8 will be 28. So if someone talked on their cell phone for 80 minutes, based on that plan, their cost would be $28. Okay. All right, here's the last example. This one is similar to problems that are in the homework on my math lab. I'll just cover those. Evaluate the piecewise function at the given values of the independent variable. Here we got f of x equal to, and we only use the 5x minus 1 if your x value is less than 3, or we use 7x plus 2 if your x value is greater than 3. So let's look at parts A, B, and C. Starting with f of 1, we want to evaluate this piecewise function when x is equal to 1. And here, x equals 1, that value is less than 3. So you must use the first one, 5x minus 1. So here we're just going to substitute the x in 5x minus 1 with 1. So you got 5 times 1 minus 1. Well, 5 times 1 will be 5. 5 minus 1 is 4. I'm sorry. Yeah, that's right. All right, now for B, f of 7. So we're going to evaluate this piecewise function when x is equal to 7. Now here x equals 7 tells us which one we need to use here, either the top or the bottom equation. In this case, since 7 is greater than 3, we need to use that bottom equation, 7x plus 2. So f of 7 is going to be this 7 times x, which is 7, plus 2. And then 7 times 7 will be 49. 49 plus 2 is 51. And finally, f of 3. We're evaluating this piecewise function when x is equal to 3. Well, let's see, we have to use the second one because it says x is greater than or equal to 3, and 3 does equal to 3, so we need to use the 7x plus 2, not the 5x plus 1, because it says x is less than, strictly less than 3. And 3 is not less than 3, so we must use that 7x plus 2. So this will be 7 times x is substituted with 3 plus 2. 7 times 3 is 21. 21 plus 2 is 23. Okay. So that's how we evaluate piecewise functions in this case. All right, so this will conclude this video on section 2.2, dealing with more on functions and their graphs. Also, feel free to email me if you have any questions about the problems that are presented in this video and the homework in my math lab.